Aloha class, it is homecoming week. I got my beads on today. I got my Chicago Cubs onesie on today. We are on the last chapter of Calc AB. Lil Holmes, Rochambeau, gotcha, give me them beads. All right, here we go. Section 7.1, integral as net change. So this kind of introduces us into a major part into the last section, the last chapter of AP Calculus. We'll get into what the topics are because the main topic here is in 7.2 and in 7.3, okay? We have already seen how position of an object can be found by finding the integral of the velocity function. Velocity is only one type of rate in which we can integrate to get a total amount of something, right? When we integrate a rate, we get the total amount of something. In this chapter, we will discuss some other uses for integration based on the idea that integration causes the product of two quantities. Example 1, considering the following statement. 2 steps forward, 1 step back. You know, a little cha-cha-cha, 2 steps forward, a little 1 step back, right? Well, what's the total number of steps? Well, 2 forward and 1 back, doing a little cha-cha. That's a total of 3 steps, right, class? What is the net change in position called, right? And that would be called displacement. So if I'm taking 2 steps forward, or little Holmes, taking 2 steps forward and 1 step back, what's his displacement? His displacement is 1 step forward. Okay, 1 step forward. Okay, and that's what we call our displacement. That's where he would be when the little cha-cha is done, right, class? Example 2. We got little Holmes. Crawling up, little homie, right? Crawling up a wall. At time equals 0, the bug is 3 centimeters from the floor. So when he starts, the little dude is already going, right? What is the bug's displacement from t equals 0 to t equals 7? Now, something important to note is I have over here that this is the velocity graph, right, class? And it's always important to know that that's velocity graph. Now, what's the relationship, right, between velocity and position? My marker stopped. I'll be right back. All right, class, I think I got it. I'm just going to have to change a page right here. Boom, not that guy, but that guy. Okay, here we go. Let's hope this bad boy works. It hasn't happened in a little bit. Ooh, and I got it fixed. All right, so that is the velocity graph. Now, what's velocity's relationship with position, right, class? It is the derivative of position. So I could write a little statement like this that we've been doing, that if I take the antiderivative of velocity, that's going to give me the position, right? And guess what? That means the area underneath the curve. So that's the relationship that we kind of want to understand when we're looking at a graph like this. Because at the end of the day, question A asks us, what is the bug's displacement from 0 to 7? So if I look here and I want to talk about displacement, what this question is asking me is from 0 to 7, how much did we travel? Okay, it'd be the area under the curve, right? That's going to give me the position. And if I look very carefully here from 0 to 3, that's a triangle. You could do a little half base times height. Oh no, don't tell me it did it again. No way. All right, class, here's our last shot at this bad boy, okay? If not, it's a new video, and I'm going to get angry. All right, here we go. So we're 0 to 7 of our velocity, which is the area underneath the curve. So if I do a little 1/2 base times height on that triangle, I get a 2. If I do a little 1/2 base times height of that one, I get a -2. I get a 3, I'm sorry, for that one. I get a -2 for that one, and I'm going to go all the way to 7. So that means I get the triangle right there. And if I do the area on that triangle, I get 4. So it'd be 3 plus a -2 plus a 4. And I get a displacement of 5. How about that? It says, what is the total distance the bug traveled from 0 to 7? Well, total distance would simply be, another way to write this, would be the absolute value. Okay, and if I do the absolute value, my velocity kind of turns this up, right, class? So that would be 3 plus the absolute value of my -2 plus 4, so that'd be a total of 9. So it's very important to understand, right, the difference between displacement and total distance, even though we've done that before in AP Calc, right, class? It says to write an integral to represent part A and to represent part B. Well, we kind of already did that, right? That'd be 0 to 7, v of t dt, that'd be part A. Okay, part B, the really fancy way is to use this absolute value symbol, but let's break it down a little bit better than that, right? We're going to go 0 to 3. If I do that, the area is going to be positive. I'm going to subtract or take the absolute value, right, class, of, but I'm going to subtract this case. So let's get rid of that absolute value. The integral from 0 to 5 via t dt. And then I'm going to add the last piece from 5 to 7 because that's going to give me a positive. Okay, it says B, where is the bug located after 7 seconds? Now, this is a little bit of a trick question. Hit pause, and I want you to write down an answer. Exit out if you got it wrong. But whenever we find, so hopefully you did that little pause thing, and whenever we want to know where something's located, and we don't use the word displacement or total distance, we always want to take into account your initial position plus your change in position or your displacement, right? So what was our initial position, right? Holmes was at 3 to start out, right? So that's his initial position. And then what was the displacement, class? It was 5. So where was Holmes? He was 8. Okay, maybe he was, here's a start. He crawled up a little bit. Oh, snap. There's a fly on the wall. Come back down and then go right back up. Okay? Displacement versus total distance, right? It's a very important topic that we want to make sure we understand the difference about. We kind of just talked about it, but here we go. Let's go again. Displacement is the net change in position. Total distance is the total change in position. When the object is moving in a negative direction, break the integral into pieces, kind of like we did up there, and subtract the value of the integral of the area under the curve. All right, example 3. Suppose n of h represents the rate. Rate means derivative, right, class? At which tickets are written by a local police department. Oh, no, don't speed. Measured in number of tickets per hour. Write an integral to find the total number of tickets written in 2 days. Well, within 2 days would be from 0 to 2, right? And my integral, here's my function right here, correct? Now, that's a rate. So that would be, what would that be? Number of tickets per hour. Okay, and then I want the change in hours, right? So what would that kind of look like? Well, that would be the number of tickets, right, class? This is kind of what's being represented here over the hour, right? Because that's our rate right there. And I'm going to multiply it by the change in hour. Boom, snap, snap, and you get an answer of the number of tickets. Total number of tickets, right, class? So that's kind of, in essence, what we're doing here when we take an integral of a rate. Okay, and that's the importance of what we're going to do here in the rest of Chapter 7. Integral as a net change. Okay, remember, integration uses a process of multiplication. Okay, just like there. And it gives me a total amount. That's what we always kind of want to remember. So if I take the integral from a to b of some rate, it gives me the total, it gives me the amount of change from a to b. Total would be if we did the absolute value. I almost use that word, right, class? And then new position, your new position is always your initial or old position plus displacement. Your new amount is your initial amount plus the net change, or right, if we're talking about amounts. We're not always going to be talking about velocity and change in position, right, class? We're going to start talking about amounts now. And that's why we have that second piece right there, okay? All right. Let's see, example 4. Oh, snap, almost guaranteed to be an AP question in some way, shape, or form. All right, the tide removes sand from Sandy Point Beach. Oh my gosh, take me back. Right, Sandy Point Beach is we had a beach back in the islands. Sandy's, it's called Sandy's. And the beautiful thing about Sandy's, it was a shore break. So it was great for bodyboarding or boogie boarding, where you literally would catch a wave and crash right onto the shore. And it's one of the most beautiful places in Hawaii, one of the best places to go boogie boarding or bodyboarding. Just remember, don't ever go straight on that wave, right? Make sure you're at an angle. If not, you're going to get hurt, right, Holmes? You go straight, crash, boom. Sorry, Holmes. All right. All right, so we're at Sandy Beach. Okay, we have, you don't have to pump sand out there in the islands of Hawaii, but this guy, I guess we're pumping sand into the beach. Okay, and it's being modeled, and it's a rate, right there. This is S of t, and where does it say S of t is here? So we have pumping sand. Oh, no. Okay, so R of t is you're removing sand. S of t is you're bringing in some sand. right? Did I read that right? R of t and S of t have units of cubic sands per hour, so they're both rates. At time t equals 0, oh shoot, there's an initial amount right there, right? So at 0, we have 2,500 cubic yards of sand. Okay, there it is. Remove sand, okay, by R. So R is remove. S is you're adding some sand to that. A, how much sand will the tide remove from the beach during the first 6-hour period? Well, that's just, hey, from 0 to 6, and we're removing, so we're going to use R of t dt, right? What I'm gonna do is I have a rate, and I'm gonna multiply it by the change in the hours, and that's gonna give me the total amount of sand. That's what we want to remember from right now. That's gonna give me the total amount of sand removed. And guess what? This is just put it into your calculator. Make sure you're in radian mode. Okay, I got the answers here to save us a lot of time, okay, class? But if you put that bad boy into your calculator, and yes, you get an AP question, this okay. It'd be 31.816. Remember, always truncate or round to the third decimal spot, and then it would be cubic yards, right? And that's what it would be. This is not a rate because I took an antiderivative of a rate. Remember, there's multiplication happening there. A rate times an hour, so it's yards per hour times hours, which gives me cubic yards. Okay. B, write an expression y of t. All right, so we want some expression y of t. I'm going to make up a function is what I'm doing here. For the total number of cubic yards of sand that's on the beach. Whew! So what do we have to do when we do a problem like this? For one, the one thing a lot of students forget is what is the initial amount? I'm going to have to make sure, and you are kidding me. Sorry, class, we're not going to let this thing beat us. There's just no way. Okay, but if you're wondering why, oh snap, hopefully that's not some test we got coming up. Oh no, Mr. Tanaka, get off that bad boy. Okay, here we go. Don't worry, it wasn't a test. All right, so here we go. We got y of t. And our formula for this, which most students forget, is we are going to have our initial amount, okay? And we're going to add to that what's going on. Now, what's going on? Well, for one, we're adding some sand and we're removing some sand, right, class? So here we go. We're going to have an integral, and I'm going to combine the two, okay? And we're going to go from 0 to t, right? Because our function here, it says, is y of t. Okay, so from 0 to t, t being the number of hours that have elapsed, and then we're going to have a quantity here. Okay, and check it out. The marker went out again. Can you finish it? Hit that pause button, see if you finish it. I am not going to let this guy beat me. All right, so it's the initial amount plus. So I'm going to save some time here, right? My initial amount, remember, was 2,500 plus we have sand that's being pumped onto that bad boy, right, class? And I also have sand that's being removed. If you notice here, yes, the variables are different, right? This is a function with respect to time, right, class? And hopefully that's going to bring something up right there that we did in the previous chapters. All right, find the rate at which the total amount of sand on the beach. Remember, that means total amount of sand. It's asking me to find a rate. So that would be y prime of t. Okay, so what the heck would that be? It's more specifically, right? Well, let's actually find y prime of t first. So let's find the derivative of this guy up here. Well, the derivative of 2,500 is 0 plus, remember, this is the derivative of an antiderivative, which means I just simply plug the t in, right? And it changes if it does change, but the derivative of t would be 1 with respect to t. So when it asks me to find y prime of 4, that is simply s of 4 minus r of 4, right? And you do all this in your calculators. It's smart to put this function in y1, put that function in y2, and then you just have to do y1 of 4 minus y2 of 4. And if you do that correctly, you get an answer of negative 1.909 cubic yards per hour, right? That's a rate. How do I know that's a rate? Hey, we're taking a derivative right there, okay? And it's important to know what that means, okay? So I'm going to write what part C means right here. This means, okay, and make sure you write this down because we have to justify a lot in AP calculus, okay? This means Sandy Point Beach is losing, right, is losing 1.909 cubic yards per hour of sand at time equals 4 hours. Okay? And you always remember, I tell you guys this all the time in class, you always want to see if you can write that in your own terms. All right, part D. Part D is the biggest part. Please stay with me, pen, please, please, please. Okay, from 0 to 6, at which time t is the sand at a minimum? Oh, that's like extreme, right, class? Can't even get into this because this darn pen keeps on messing me up. Come on, let's go, homie. All right. So whenever it's extreme, ask me a max or min, then, oh, and I have some endpoints, right? There's a lot of things I have to check here, right, class? And there's a lot of work that I have to show, all right? But we want to know when y of t is at a minimum. Well, if I want to know when y of t is at a minimum, okay, that means I have to find the derivative, right? Because derivative, we find critical points, and that helps us to find mins or maxes. Okay, so let's go ahead and find the derivative, right? But I did this before, correct, class? The derivative of 2500 was 0, and then it was s of t minus r of t. Okay? And I'm just going to make sure I get through this bad boy. All right, so we need to know the critical points of that bad boy. Well, what the heck are the critical points of that bad boy? Well, let's use some algebra 2, some pre-calc, some of what we did this year. But this guy is going to be 0, hopefully you notice, whenever s of t is equal to r of t. So what I want you to do, hopefully you did it already, but put that in your calculator as y1, put that in your calculator as y2, and we want to know when they're equal to each other, and they're equal to each other graphically where they intersect. Okay? And those two guys will intersect when you do it in your calculator at, intersect at t equals, I got it right here, 5.117865 tree, and then what are you going to do with that? Hopefully you say it. You stow that bad boy in A. Okay, stow that. Remember, you do not round in AP Calc until you have a final answer. Okay, so we're going to, don't worry, class, if I lost you a little bit, this is some really tough stuff. It's the toughest part about this AP question, and we will do more of these in class. Okay, but you store that in A. Now, that could be a minimum. Okay, now how do I check this? Well, remember, that's my critical point. That's my only critical point. Why is it a critical point? My pen just ran out. You got to be kidding me. It's a critical point because that is when the derivative equals 0 or DNE. How did I know it equals 0? Because s of t minus r of t will be 0 whenever they're equal to each other. Okay, now guess what I have to do? Hit pause. Told you, class, it's not going to beat me, and I'm going to get done in 20 minutes. It's not going to beat me, okay? But let's go leave off where we just were, and we have critical points. So we have our t's here, right? And we have y of t right here, right? We always plug these into the original. And we have 0 and 6 are my endpoints, and then we have where we stored that value of a, which again was 5.117 truncated, but don't truncate it. Or round it until we have a final answer. So then now all I have to do is plug these guys in. If I put a 0 into my y of t function that we had up there, it'd be 2500. If I plug an a in there, so we're going 0 to a, I get 249.277. And if I plug a 6 in there, oh, shame on me. Ooh, that is, let's erase that bad boy. This was for 6. Oh, no. And A was this. Okay, it was different in my notes. 2492.369. Is that a minimum, class? For show? It is, right, class? So the amount, come on, stay with me, marker. The amount of sand is, because remember, that's the total amount of sand right there, is 2492.369 cubic yards at time equals 5.118 or 117. And there we go. That's an AP question. If you understood that bad boy, we're going to do more in class. I apologize for the delays. It was a little crazy, but I'm not redoing it. And still in under 20. Go Indians at homecoming. Shaka, shaka, shaka. Let's do it right now. Right? Rochambeau. I'll do rock, paper, scissors and see if you can beat me. Ready? Rock, paper, scissors, shoot! It's a paper. One more time. Whoever wins this one, if you can beat me on this one, you get bonus on the next quiz. Ready? Rock, paper, scissors, dynamite! Just beat all you guys. Peace. Aloha. See you later.